Hello, my name is Simon Lang, and today I want to talk about ensemble forecasting with AIFS. So, one fundamental thing about the atmosphere is that it's a chaotic system. So, this means that small errors can grow to have a major impact. And we can also never perfectly measure the current state of the whole atmosphere, so this will always be an inherent issue. And this is here visualized with the famous dynamical system by Lorentz. Um, so here, for example, you have a trajectory or trajectories where your initial conditions are close together, and then over time, when the forecast progresses, they actually stay relatively close. But then you can also have situations where you start similarly close together, but then the forecast uncertainty grows over time. So what stayed close does not stay close further out. And in the extreme case here, you have a situation where you stay close together, but then quickly you lose all kinds of predictability. And this just visualizes how important it is to also have a measure of forecast uncertainty associated with your forecast. And in fact, this also applies to the atmosphere, as I said. And usually to quantify forecast uncertainty, here we run ensemble forecasts, which means a parallel set of forecasts from very slightly different initial conditions and a slightly different model formulation. And this then lets us assess the uncertainty associated with the forecast. Again, an example here on the right. This is a situation here in black is the analysis, so the truth, and light blue the single deterministic forecast, and then in red the ensemble members. And up here you can see that even for over the first days of the forecast, all the members stay reasonably close together. So you would expect low uncertainty associated with the forecast. And then you can have situations like depicted down here. All of this is, I think, 2-meter temperature, where after couple of days, you get a very large spread, so very different scenarios playing out. And yeah, predictability in this situation is low. Another way to visualize this is with a tropical cyclone forecast here, which recurves over Japan. And again, in the example here, after even a couple of days, you have very wide uncertainty associated with the tropical cyclone track, which depends then also how the tropical cyclone interacts with the extratropical weather systems. And then a couple of days later, this track spread collapses much more, and it's much more certain where the tropical cyclone will pass by. So the problem is basically we start from an initial PDF, and then we have to propagate this forward in time. And this is determined by the dynamics of the system we're looking at, but also by our model formulation and errors associated with our model formulation. And that's basically what the ensemble forecast is about, to propagate our initial uncertainty to a future time. One important aspect of ensemble forecasts is the reliability, or here the reliability of the ensemble spread. So if we consider ensemble variance for a ensemble here and the squared error of the ensemble mean, then if we average these two quantities for many locations and or start times, then on average they should match for a reliable ensemble within sampling uncertainty. Also, then the assumption here is to have an infinite ensemble size and no observation error. But actually for finite ensembles, we can compute corrections for both these quantities. And here on the right, again, a picture from our physics-based ensemble system, just to show how this spread error relationship developed over time. So we started from a rather unbalanced system to nowadays a very well tuned or calibrated system. And yeah, I think these are plots here of wind gusts, again, from our physics-based system. And on the right is our control forecast, so our single forecast. And then on the right are the one perturbed member. And if the one thing you can see is how rich the dynamics are. And the second thing when the forecast starts again is that you can see that initially both are very similar and then they start to diverge over time. And that's exactly what we want to capture with ensemble forecasts, because this allows us then to associate uncertainty associated with the forecast. Just wait until the animation finishes. So when we talk about weather forecasts, physics-based, NWP, data-driven, what does it mean? And I think you have heard already quite a lot about this in this course, but just a quick recap. So traditionally, weather forecasts are generated by running an NWP or physics-based model, and that's really computer code designed to represent the physical processes that govern the evolution of the atmosphere. But one question that came up recently, and what this is here about, is can we forecast without such a physical-based model as well? So again, to recap, the analysis we're talking about is a fusion of a short-range forecast, usually from an NWP system, and that is fused with the latest observation, so that gives us a good guess or a good estimate of what the current state of the atmosphere is. And then with a physics-based system, you can start from this and produce a forecast. And then with a data-driven system, the question is, can you learn actually and replace this physics-based system here by learning from, for example, 40 years of reanalysis data? And recent advances have indeed shown that this is possible. And how it works is that the model steps through these 40 years of analysis data, always like 6 hours, for example, at a time, and learns to forecast how the atmosphere evolution is within these 6 hours. And then you build from this basically a forecast model. So if you want to run the forecast, you can then just, the model can just forecast the next 6 hours and then start from its own prediction. And then you create an autoregressive rollout. And the model we are using here is or I will talk about most is here, the AIFS, which has an encoder processor decoder architecture, which basically means that we start from the full resolution atmospheric grid. We encode to a lower resolution internal grid. We have a processor here that runs, for example, 16 times and then writes out via the decoder again the full resolution grid. And that would be then one forecast step. And then you would initialize again. And yeah, if you probably have heard, this works quite well. So you can produce very skillful forecasts with such a system. But one aspect you encounter frequently is that these forecasting systems tend to smooth. So on the left is the IFS forecast of the physics-based system. And what you can see is that the statistics don't really change with lead time. So after 12 hours, the forecast looks basically like a forecast after 10 days. So the same amount of small scale structure and variability, of course, condition the actual forecast situation. While this is not true, for example, AIFS, which has been trained with a mean squared error loss, a deterministic training. So here you see that after 12 hours, there's still quite a bit of small scale structure, but then it loses more and more structure over the time of the forecast. And that limits its ability to produce ensemble forecasts because it can't really reproduce the variability of the atmosphere. And that hinders it basically to produce the right amount of ensemble spread. So the next logical step is how can we actually train a model which can produce this variability and can produce realistic forecast states at all time. And again, just to recap for the physics-based side, how we usually do it is you have an ensemble of data analyses. So you start with short-range forecasts here in blue, and then you fuse them with observations where you assign an observation error, which is then the outcome of this is then these green trajectories here. And then you can use these to start your ensemble forecast from. But in the machine learning world, we have different approaches to actually construct such an ensemble forecast now. And one option is to, instead of using a mean squared error loss, we learn a ensemble via optimizing a probabilistic score, such as the continuous rank probability score, CRPS. So here you bring forward a small ensemble in time, and then you have a probabilistic loss that ensures that, or that encourages the model to learn the right forecast distribution. And the second very popular approach is to create a forecast via a denoising task, such so-called diffusion models. And these are very popular in all kinds of areas, such as image generation, video generation, and also have been introduced to weather by, for example, here GenCast. So I will first talk a little bit about the diffusion training and then later about the proper score optimization. So for diffusion, you have a forward process that adds noise to the forecast. So you start basically from your forecast tendency, for example, that brings the current state to the next state 6 hours later, and then you add noise to it until you lose all signal, and the model then learns the reverse process. So it learns to create a forecast tendency out of noise condition, for example, on the initial condition. And because the model doesn't have to do the full step at once, but can create these intermediate states where it's conditioned on already partly denoised states, it can then generate realistic structure. Where you pay for this is that you have to run a sampler in forecast mode, so you can't, you don't run the model once, but you run the model multiple times for each forecast step. For example, 40 times to slowly create your forecast tendency then out of the noise. And for example, this means that for a 12-hour forecast, for a 15 days forecast is a 12-hour step, you would call the model 1,200 times. However, what you benefit from is then that you get a realistic looking forecast. So here on the right is AIFS trained with the mean squared error loss. Again, you can see these smoothing, and on the left you see how the diffusion training performs. So you see that there's lots of small scale structure and you don't see really these statistics change over the time of the forecast. So an alternative is to train a model probabilistically via a so-called proper score. And here we use the continuous rank probability score. And as I said, you don't train for each set of initial conditions. You don't run a single model, but like a small ensemble, for example, 2 ensemble members. And then you compute this loss here. And yeah, you compare against the truth via this loss. And the CRPS-based loss has 2 terms. So the first one here you can see is like a loop over the ensemble member. You compare ensemble members to the truth. So the members should be close to the truth or the observed state. You encourage the model to do that. But then you have a second term balancing the first one, where you also compare members against members. And the difference between ensemble members should then represent the forecast uncertainty. So this prevents the model to collapse on a single solution, but you have to create, to produce a good forecast here, the model has to create realistic variability and to stay close to the truth. And yeah, the question is, how well does this work? Because of course now the model has a very difficult task. It has to do it in one step. But to show how it fares is here we have the ensemble members of the AIFS ensemble here, member 1 to 4. For comparison, here is the single AIFS single trained with a mean squared error loss here on the right, and then the analysis for this time is here, and what is shown is wind speed at 10 meters. And I think you can nicely see that the different members really maintain their variability within the forecast. So there's no drift or anything like this visible, like you see in the AIFS single, where it goes from some structure to this nicely smooth world. And yeah, if you compare to the analysis, also these members look much more similar in terms of variability to the analysis. And what you can also see if you look closely is that all the members look initially similar and then diverge over time. And this is easier to see when we stop the animation here. So member 1, 2, 3, 4, all of them look a bit different, have a bit different weather systems at different places. Here, after 50 days, lots of the predictability is already lost. And yeah, you can again compare against the AIFS single, which is much smoother, and the analysis, which looks very close to one of the members. So we can see that this CRPS-based approach really works here. And again, another way to look at it is when we look, for example, at precipitation fields here from our EC charts, you can see that the AIFS single here is much smoother than, for example, a member of the AIFS ensemble, which has much more small-scale energy, which is closer to what the physics-based system also shows. However, one challenge for this CRPS-based training is that we compute CRPS really point-wise. So the forecast really informed by the members at one grid point or at the different grid points, but there's no measure or no information about the scale of the problem. So in principle, the model can overcompensate for variability, which is missing on the large scale, on the small scale, and vice versa. And scales are very important for the atmosphere. It really, different scales contribute in different ways to the loss. So one attractive way to make the model more scale aware is really to introduce scales into the loss function. And so just to show, for example, when we have here is a very coarse scale, right, where you see the large scale systems or the large scale structure of the atmosphere, and then you can have a scale which has more small scale structure, and then one scale is even less or even smaller scale structures. And here to make the loss scale aware, we do this via a Laplacian cascade. So we can now compute CRPS for each of these different scales and then aggregate, and then the model can decide what variability should live at what scale. And yeah, this is again to show how this works in practice. Again, here, for example, the true target field, then here a smooth version of this, which would be your scale 1. And then the second scale, for example, the difference between this smoother scale and the full resolution target. And when we train a model like this, compared to a model without the scale awareness, we see that it can help to reduce small scale noise. Here, for example, the model on top has been trained without any scale awareness. And you can see these wiggly structures here in the ISO lines, which means it produces too much small scale variability, while this is really counteracted as soon as we have the scale aware loss function. So how well do all of these approaches work, or do we actually get a very skillful model by training like this? And the answer is yes. So here, this is a score card comparing the AIFS ensemble with the AIFS ensemble for 2024. And here on top, we compare different variables against analysis of the physics-based model, and then here on the bottom against observations. And blue means the AIFS ensemble performs better. And yeah, you can see that the scorecard is very blue, so it performs quite well. We see some red at upper levels, which is associated with how we design our loss function, which is really focused on lower levels in the atmosphere. But yeah, overall, you can produce very performant forecasting systems like this. The caveat is here that this on top is mostly focused on the larger scales. So the AIFS ensemble is not run at the same resolution as the IFS ensemble here, which has 9 km resolution, and the IFS CRPS ensemble here has more like 30 km resolution. And to show this even more is here we compare the IFS ensemble against the TIGI ensembles, and that's a database of ensemble forecasts from different global ensemble forecasting centers, for example, ECMWF in red, but also the German Weather Service here and so on. And you can see in red the IFS ensemble, which traditionally is a very strong system. But then if we plot the AIFS ensemble, then you can really see that this is a further steps change from that. So a very skillful system. Yeah, and what's shown here is continuous rank probabilistic score for 850 hectopascal temperature. One interesting property of the system is that you also can produce very skillful longer range forecasts. So that is really an emerging property. You train on very short range forecasts, or you train on the very short range, like up to 3 days. But then if you run a forecast for months or longer, you still produce very skillful forecasts. And that's just an example here for the MJO. And this is here a correlation index, so higher is better. And you can see that a variant of the AIFS ensemble here can even outperform the IFS ensemble. And here we have a spread error diagram as well. And interestingly, also the spread and error of the AIFS ensemble seems quite well balanced. And this is also another visualization of this. Here, these are Hofmöller diagrams. So here you see the history on top of the forecast, the true states, and then how, not of the forecast, but of the atmosphere. And then down here is the forecast. And this is here the truth for the whole forecast period. And you can see that here these anomalies here, how they propagate, are well captured by the IFS ensemble system, AIFS ensemble system. One thing to really watch out for when developing such systems is that they don't have an inherent representation of physics. So one thing we could see when we put the first system into operations, actually later we realized that it can produce quite unrealistic structures at some places on the globe. So this is a measure of variability here. And you can see after 15 days that close to high orography, there can be ensemble members which produce very unrealistic, unphysical values. And we could actually get rid of these in the version 2. But yeah, it's really just a reminder that even when the large scale scores look nice, you really have to look into detail and at all the variables to check that you don't suffer from forecast artifacts. One thing is now that all these forecasts from our physics-based model and also the ensemble model are now on easy charts. So if you're interested, you can go and compare the two systems. I think that's quite nice, and learn also about their properties and how they differ, what they do well, what they do less well, and use them to produce forecasts. So yeah, AIFS single and the AIFS ensemble are now operational. And also all the model code is open source. So you can go to GitHub and look at the source code. And also the model weights have been published. So the still version 1, but now the version 2 version model weights are also available. And yes, so that's the last slide for me. So the question is, what's next? For these systems, we want to go to higher spatial resolution and higher temporal resolution. So that's really still quite a difference here to our physics-based model, which produces many more output variables at higher spatial and temporal resolution. And for that, we also anticipate we have to improve the scalability of our machine learning systems. We want to look at even longer time ranges and also importantly, integrate more of the Earth system components like atmospheric composition, the ocean, and so on. A big topic is also to improve physical consistency, which is an ongoing endeavor. We already made quite good progress, but yeah, there's more to do. And then one big topic will also be to start to exploit observations directly. So far, we tend to learn from reanalysis data and analysis data, but there's of course the option to also then in addition bring direct observation data in and help the model to forecast better at observation location or learn from observations to produce better forecasts. And that's everything for me. Thank you very much for listening.